Okay, that link gives you the summary of syllabus, office hours, test days, and what are covered in each test, chapter 1 and 2 for the first test, right? All right, and when is the comprehensive makeup going to be? Then you correlate all this with the calendar, right? So everything is, I proofread. If there's anything missing or incorrect, let me know, right? I mean, I'm not a 100% perfect, okay? I don't want to say I'm not a perfect person. That's a catchy word, right? I'm not a perfect person means then I'm imperfect, all right? But I'm not saying that. So I'm like 75%, okay? All right, required tests are here. Mastering the test book, with this one and the mastering, okay. To get to the Moodle, this is the address, or go on to tech web page, press on the Moodle. Optionals are this. If you're a student athlete, you can get it from the athletic department. I will sign that you're taking the class. Most people come and ask me to sign, right, in previous classes. Now this is the table content. There are a lot of material, but it's pretty simple. We're going to talk about atoms and molecules and scientific method and the classification of matter today. Up to, in this group homework, that these are the three, section 1 to 3, we're going to learn. Then other one would be that, and the rest is going to be here. All right? 3 group homework going to be. Group home, second is the middle part, we're going to cover. I wrote down, these are the key concepts. Just browse it after you go on over the material, whether you know what they are, definitions, and whether anything that left out here, right? Okay. Now, first question is, what is chemistry? There are a lot of answers. What do you think what is chemistry is? This is kind of boring, non-reversible changes of matter, right? What do you mean by that? There are reversible changes, irreversible. For example, if you take water, if you freeze it, it becomes ice. Is it reversible? If you take out heat it up, you go back. And you take the water and electrolyze. What do you mean by electrolyze? How many of you know what that means? Electrolysis of water, you put that in a beaker, all right, and connect the voltage, high voltage, okay, and positive, negative, and the hydrogen gas and oxygen gas is coming out here in 1 to 2 ratio, right? Now, once you electrolyze, you cannot passing a current opposite way. Can you produce water? No. It's kind of irreversible. In a way, you cannot directly undo the change you did. Okay, whatever the thing that you made, that change, like heat or electric current, in this case, reversing will not do it, right? So normally, physical changes like ice to water to ice is called a physical change, right? The matter in this case is the same in water. Water going into the solid, that's the ice, water, ice. The matter remains the same. This matter, I mean substance, right? Matter is made out of substances, right? We're going to talk about this more. Substances of the matter remain the same in physical change, but in a chemical change, they are completely different. Water is different from oxygen. It's an element, right? It's a compound, converted into two elements. So that is the substance change. Normally what we do is in chemistry, we use the idea of atom, molecule, and ions. This book left out ions. I mean, if you look at certain matter, they're not molecules, they're not atoms, they're ions, like sodium chloride, right? So I put that in there because it's kind of misleading. Okay, ions. Then we have models, right? And like theories, atomic theories, and a lot of, depending on the area you are in, chemical kinetics, gas laws. For gases, we have theories, right? Concept. We deal with that, explain their properties. Then equilibrium. So equilibrium reactions. We have concepts. We're going to learn gradually. Going through these 3 chemistry courses for most of you: 100, 101, and 102, right? Okay. As I said before, chemistry is a central science. How many of you understand this wording? What is a central means? Central means this area of knowledge used by many other areas, the applied areas of the sciences, right? So industrial engineering is not a central science, all right? Because we don't use it, but we are kind of more in the fundamental state. So everything develops up, okay? The medicine, mechanical engineering, and biology is also central, right? Biomedical engineering. So how many of you are here biomedical engineers? Only 3? I thought it was the most popular, major on campus. Isn't it not? How many of you are biology majors? How many of you are chemistry majors? Great. All right, we will be seeing you. Okay, a lot more. Okay. Anyway, if I didn't cover other majors, there are many. Okay. Biology, chemistry, math. Do you have any math majors? No. All right. What is atom? The idea is matter could be divided into smaller pieces, right? That ultimately matter could be, if you take a piece of copper or gold, you break it up into tiny pieces, eventually you end up with a indivisible. Atom means indivisible, right? Greeks, atomos was indivisible. So that's what the atom is. But it's a very small particle. You cannot see it with your naked eye. If I break a small piece of paper, like this, like this, like this, I don't have to take the bigger piece. I get the smaller piece and break it up. Then how many times? They calculated, how many times we need to break up a paper. Like 50 times in a small piece of paper. You might get close to 150 times. So I forgot what the calculation was. You can break it up if you can, right? Most of the things, macroscopically, we cannot reach atomic level anyway. Okay. Different types of atoms have different chemical properties. Therefore, elements have different properties. Also, when they make up molecules. What is a molecule? Normally, that word stands for collection of atoms bonded by covalent bond. I mean, I will talk about that. We will be learning about covalent bond later. It's bonded by sharing electrons, right? So, like water, oxygen, and or nitrogen atom, nitrogen molecule, nitrogen. Now, we also call molecules. Sometimes we define it. Smallest particle of an element, that exhibit their properties. For example, if you take nitrogen, the smallest particle is nitrogen, N2. But the helium and noble gases, smallest particle is 1 atom of helium. Except for those, the molecule is the group of atoms. It could be compounds. Compound, what is the meaning of a compound? What is a compound?
2 or more elements bind together.
Right. Two different atoms forming like a water, right? It's a compound. So you have to understand. And losing or gaining atoms can lose or gain electrons and form cations and anions, right? Then they attract each other. Atoms and ions determine how matter behaves. Not only atomic properties are important, also in combination with other atoms, they change the water is different from hydrogen and oxygen, right? It's not the average of properties, right? So more combination they make, they also change. Now this is interesting. Biology is very complex, molecules in biology. So life is maintained by all these biochemical pathways, molecules and all that. So the more complex a molecule can get, the more different it's from the elements, right? So therefore, matter is shaped by the type of atoms found in the matter, also the way they bonded to each other. So for example, sodium chloride has ions, electrical conductivity. You can put it in water and you have a solution which conduct electricity. And you can have a metallic element like iron or sodium, magnesium, calcium, all these black the black elements on the periodic table are called metals. When they are themselves, like sodium atoms, by themselves, together make a metallic compound. Metallic element. Compound is a metallic compound is a alloy, like bronze, steel, stuff like that. So anyway, what you would say, atoms and molecules are determined how the matter behaves. If they were different, matter would be different. If their properties depend on the type of atom, the way they bonded, right? So structure of the matter. Now we use models. Atom is the smallest unit of element that has all the properties of an element. For example, nitrogen. Element is N2, nitrogen molecules. But if you break up, nitrogen is the smallest particle, right? 2 atoms. Molecule is the smallest particle of a pure substance that has those properties of that substance. Now, molecule is a neutral entity, all right? The neutral entity. So you need to see ionic compounds are not molecules, right? They're made of ions. Ions are the charged particles, ions are found in ionic compounds like sodium chloride. They lose or gain electrons. I need to write down the difference. What is the difference between okay. If you take sodium chloride. That's an ionic compound. Ions are there. Now, if you look at the structure, you have positive ones, that's positive and negative ones, and then there's no electrons in here. In the metals, electrons are not valence electron. I'm talking about electrons are not in the one of the atoms. They're on the outside, shared by everything. Therefore, metallic bond has special properties. How many of you understand metallic properties? They conduct electricity, they are malleable, ductile, all these properties associated with it come from the structure, right? So metallic compounds are, metallic elements are also part of the matter, right? So we can find molecules, we can find ions in ionic compounds, metallic elements or alloys, metallic compounds like bronze. What is bronze? Copper and zinc? Okay. All right. Now, if you look at this one, this gives you a picture of what I'm talking about. It looks like this one has its own life. Okay. Now, this is an atom or molecule? Molecule, two atoms. It's called heteronuclear diatomic molecule. It's like a funny name, right? Heteronuclear means two different nuclei, right? So that is triatomic molecule. Now this is a structure. Do you know these two have completely different properties? Carbon monoxide is poisonous. It can go into replace the oxygen in the hemoglobin. We're going to talk about it a little later. And carbon dioxide is completely different. Yeah. Even the number of atoms in the group, will change the properties, right? And this is diamond, like a crystal. This is series of diamond is bonded to each other three-dimensionally. Very hard material. It's also a regular arrangement of atoms in a solid state. Means to crystals. Crystals are regular arrangement of atoms in a solid state. So crystals have shiny faces. Even the sodium chloride is a crystal, right? It's made up of cubes of sodium and chloride ions, right? Sodium and chloride ions packed in a nice way. Hey, here. I got that. Now this is a metallic element. In a metallic element, only one kind of atom is found. They also pack like this. What is the difference between these? The electrons are all around the atom, right? Sea of electron idea coming from that. So I'm trying to show you some pictures, not only the words, right? Okay, what is allotrope? Allotrope is a word that we use for some elements. Because of their structure, they have the same atoms of an element, like carbon, can have different structures and different properties. This is diamond, just like three-dimensionally bonded. This is graphite. It's two-dimensionally bonded carbon, graphite, hexagons. And this is the buckyball. It was discovered by Buckminster Fullerene. These are three different types of, three different allotropes of carbon here. Phosphorus have several, right? Oxygen has how many allotropes? Two, oxygen and ozone, right? So you can find among, because of the structure, not only the atom, structure also create different properties. That's the key idea here. Now we can show structures right down on the board. This is the structure of the aspirin molecule, and this is the ball stick models. This is the space filling models. This is hexane, not hexane, ethane. Methane is 1 carbon hydrocarbon, 2 carbon hydrocarbon is called ethane, and that's the space filling. Space filling model only shows the volume of all the electron clouds. Okay, here only bonds are shown, the ball and stick. It's not. This is more close to what it is. Okay, space filling, but it's cumbersome. You know, if you have one like that, you know, right? But this is more for chemistry. We use more ball and stick model. Hemoglobin is found in platelets, that red material in the blood, right, caused by platelets. They have hemoglobin. Platelets have hemoglobin. And what is the function of hemoglobin? Oxygen. Okay, I'm not going to talk about that too much. This is the carbon monoxide. Carbon monoxide can irreversibly, that means once the carbon dioxide get into the ion group, there's an ion here, somewhere here, ion. See, that's the oxygen bond here. It can be replaced by carbon monoxide. That's the carbon monoxide poisoning. So normally oxygen comes out at higher partial pressures in the lung. The oxygen absorbs oxygen, and the hemoglobin absorbs oxygen, and at the muscle where the partial pressure of the oxygen is low, they release it, right? So this is all based on a kind of giant molecule, right? We call hemoglobin. So the biological structures, enzymes, and all that, you know, are made out of atoms. Different way they are bonded, right? Create complexity, right? Now is the time to answer a few questions. Okay, identify the names and the atoms, molecules of ions with charge. If they're ions, they have to have charge. Form from the following elements and compound express their properties. What is identify the name of the atom? Name of the atom. What is the atom here? Nitrogen, right? We call it, that's a symbol. How does these properties, nitrogen is a gas. Why is the nitrogen gas? Because there are no attraction between nitrogen molecules. Water is a liquid, right? Because there are dipoles in the water, attract each other. So potassium, atom is a gas. No inner molecule. Do you understand what I'm saying now? Potassium, what is potassium? Atom. Atom is, okay, this is same as that, K, potassium. And what kind of element, the properties? This is metallic. Why is metallic? Now when you have only metal, like black elements in the periodic table, they by themselves always make that sea of electrons, right? Therefore they have different properties, right? So it's metallic. If you have to write it down, so I will write down these electrons are outside. Okay, maybe there are other potassium ion here. That's the core of potassium, and their electrons are all over. That's all. We normally put a cloud of electrons and embedded in it, cloud of electrons, like this, and the atom. That's the metallic property. Iodine is just like nitrogen, but iodine is heavy, right? Because of heaviness, that's the atom name is iodine, same as that, iodine. It's diatomic molecule, that's a diatomic. This is also diatomic. What do you mean by diatomic? These are homonuclear diatomic, and iodine is solid because of what? Attraction. We call it London dispersion, right? London dispersion. We will learn that later, okay? Have intermolecular. All right, this is a gas. This is a molecule. This is a I need to write this. Metal is special from all other things. Metal is not a molecule. That's no covalent bond. You understand that? Metal by itself is a metal. All right. So this is a molecule, and you got to understand this. This is not there. This is same as that. Okay. But in this case, plus plus. Why is that? Magnesium ions are problems. All right. So we talked about basic idea that we describe atoms, molecules, ions, right, and metals. Basically, those two types of matter that our chemistry is based on. We also looked at the answers to questions, looking at the formula and describing what kind of matter is that. They're composed of molecules, ionic compounds, ions, or metallic compounds, and all this stuff. Okay. Today, the topic is going to be scientific method. Okay. How many of you had any introduction to scientific method before? A lot of you may have. Okay, good. Now, this is where the science and the other things separate. Science only follows this, right? If you need to make something as a science, you have to have this message in every step of investigation. Right? What we do is we try to explain things, and we want to find cause and effect for things, whatever we see. So therefore, we have to follow the scientific method, and chemistry is the science, biology and all other, even applied sciences follow this. Okay. Now, first thing what we do is these two things, either observation or experiment. Now, observation is you walk down the street, you see something happen, it's done by somebody else, right? Nature or somebody else. So you look at that. Wow, what is that? So then you come up with the hypothesis. Okay, that's the idea. Or you have somebody have a question. Would that affect? What would affect the? One example I've seen is like if you play music, would the plants grow better? Something like that. So now you have to do an experiment, right? And doing experiment involves the idea you have to have a independent variable. Dependent variable is the one you're changing, right? Then the plant growth is the dependent variable. Music is the independent variable, right? Then you have to have all other variables fixed. That means you have to have a control experiment, right? Control experiment also, we compare whatever you're doing with one that we don't have that variable, independent variable, no, dependent variable included in there. We always have control experiment. All right. Now what we do is this. We have, therefore, observation and this thing together, experiments, and you have data. Sometimes we call it data. Data come from experiments or observing the nature. Then you come up with the hypothesis. Hypothesis is something that you guess, right? You think that is what's causing, right? Then you have to do a confirm. If your hypothesis is supported by consistently, always it's there, not one-time deal, right? Always when you change the variable, that relationship between independent variable and dependent variable is always same, then you can say this hypothesis explaining that behavior is become a theory, right? All right. So point is, hypothesis is always a trial theory. So the point is, if other experiments work is not explaining properly the experiments, then you have to change the hypothesis, and then you change the theory, all right? And also data here, data. Observations are data. Could have a pattern. A law, scientific law is not a theory, all right? Scientific law is about data, like Boyle's law, Charles' law. There are laws, okay, in a theory, not in a theory. The laws explain the patterns in. I will go through that. Therefore, basic idea is you always going to have experiments and experiments, data, laws, and hypothesis, and theory, and further experiment. Sometimes we call it experiment or further experiments. Right? These are the few things that you see in a scientific method wherever it is followed. Law is a generally observed occurrence in nature, like Boyle's law. What is Boyle's law? Right. P1, V1 is equal to P2, V2. That's a mathematical form of that. So what we say is pressure of the gas is inversely proportional to the volume of the gas, right? Based on that, you derive the equation, right? Okay, let's see this. I'm going to explain something. Sometimes observation results, data, same observation, lumped up hypothesis for the experiment. Now, let's apply this to discovery of penicillin. Okay. I wanted to show you Who discovered penicillin? All right. I even misspelled his name. Images. All right. I wanted to look at his petri dishes. Okay. Let me explain this. Then make it bigger. Okay, that's all I can make it bigger. Right. Here. He was doing an experiment with bacteria. These are the bacterial colonies growing here. And his petri dishes had these bacteria growing. He's a biologist. So one day he saw a mold. This is a mold. That's called penicillium. That mold is called penicillium. How we get the name penicillin. Right. So around this area, nothing grew. So that was his observation, right? And what did he come up with? What is his trial hypothesis?
Kills bacteria. Kills the bacteria.
Say that louder.
Penicillin kills the bacteria. I mean, it is antibacterial.
All right. Penicillin, like we don't know penicillin that time.
Okay.
Okay. What he said. Somebody can explain. We go back to history. If you were Alexander Fleming, what do you say? Something that came out of that mold is kind of fungus, right? Something that came out of that fungus inhibitor. That's the name for if you grow profusely. That is not inhibition. Inhibition means growth is affected. So something that some substance that came out of that mold killed or inhibit the growth of bacteria. Now later, that was the thing. That particular experiment was only for molds. Then how it became a theory is there are substances that can inhibit bacteria, growth of bacteria. They could be coming from mold. They may be coming from other sources, right? That substance was called antibiotics, right? So penicillin was the name. Then theory of antibiotics came about, right? So further experiment expanded, definition. There are classes of what did I say? Antibiotics, right? Okay. So there are sulfur drugs, all that stuff. Okay. Important thing is that the steps. Okay. Substance secreted by the mold, inhibition bacteria mold, growth of bacteria, all penicillin was isolated. So they crushed the mold and isolated substance, and they used that liquid. All right. So that's the beginning of antibiotics, use of application. Right. Okay. You got it. What are the key steps involved in scientific method? Can you say one? I'm going to write down.
Observation.
Okay.
Observation.
I think observation is very important, right? There should be an observation or experiment. I could have written it separately, but I could have. And data, probably. All right? Data and observations are related. And what is that? Hypothesis. Okay, what is the next way?
Theory.
Now, it loops. Okay? Science is not a final word. All right? So we had so many theories before, but they were modified to explain the new ideas, right? Okay. Okay, that is the idea, right? So how many of you got the basic idea of what the scientific method entails, right? What is a hypothesis? And give an example. It's a trial guess, trial explanation, trial guess. It always kind of you don't know what happened. It's not to explain the data. There's a concept here, right? It's a concept. I mean, everything is a concept. I mean, even idea is a man, it's a concept, right? But eventually we don't think about it as a concept. But because man is well known. But when you have these things unknown, then you have to create a concept, right? To how to deal with it. So then what is the example? Let's just stick with Alex and Fermi. What would his trial hypothesis would be? Something secreted by the mold inhibit okay. Now it could be later we're going to talk about atomic theory. There was kind of in developing atomic theory, there was observation that in a chemical change, in a chemical reaction, mass is always same as before. That's called that's the observation. So what is the trial theory? The matter of mass is same before and after. So therefore matter is made out of atoms, right? Which are not destroyed during the chemical reaction. Yes?
What's the word after something?
Something secrete can, what is my meaning? I may have it wrong.
I think it's right.
Secretion is kind of saliva secreted, okay? I have my language problem, but thought it was the right word, okay? I mean, it's not a usual word. It's something coming out of something, a liquid form, it's a secretion. All right. Okay. How does the hypothesis become a scientific theory? For the experiment, confirming data and the explanation. I mean, this is the best explanation you have, right? I mean, if somebody came up with a better explanation, for that, then you can change the wording or whatever it is. Some explanation may not have real connection to that, but it has to be explained in the data, right? So it becomes, how does, what is the theory now developed by him? Theory of what? I'm not a biologist, but anyway, theory of antibiotics, right? So antibiotics is there are substances that can be used as inhibitors for bacterial growth, and then that's a general term. It's coming from bacteria, the mold. It could be coming from plants, right? Some plants have the antibacterial properties, right? Materials. So that so this theory predicted there could be other sources other than the mold. All right. So therefore, it's powerful. Theory predicts, further discoveries. Okay. Kinetic molecular theory of gases. This is a theory to explain. This is a theory. This is not a law. Kinetic molecular theory is to explain gas behavior, behavior of three states: gases, liquids, and solids. Why they have a shape? Gases don't have a volume. I mean, it fills up the space of the container, but the liquids go to the bottom and take the shape of the container, the bottom of the container, and solids will remain acidic. Now, this is for theory, kinetic molecular theory is the idea, explaining gases. This is the idea here, to explain Boyle's law, Charles' law, right? Gay-Lussac law, ideal gas law, all these things. Do you understand what I'm talking about, gas laws, right? They're experimental observation, correlations between volume and the pressure and the temperature, right? Okay, right. To explain that, we say particles are continuous. Particles are in constant motion in gases. Collision between elastic, that means they don't lose energy, otherwise we have a problem. Collision between, because the energy will lose as they collide. Volume occupied by the particle is negligible, because ideal gas law requires that. Otherwise, we don't have one equation for any 1 mole of gas at 24 liters of volume, right? Regardless of material. If you have bigger atom, then the volume should be bigger. So it's not the case. To explain everything, we relate the idea. This is the concept. That there are no forces between particles of gases. They're completely free. And gases have no fixed solid shape, take the volume in the container. So these are the theories, and these are the postulates. Now, what do you mean by postulates of theory? A theory will have several parts, like a Newton's theory of motion. I forgot what that is. Like force is equal to acceleration, right? What's that?
Mass times acceleration.
Right. Okay. Then there are 3 laws. I forgot other one. Other one is body in constant motion, right? Yeah, stay in the motion. The other one is everything has a reaction, action and reaction, right? So those are postulates. There are 5 postulates. So postulates are the breakup of theory, right, into several postulates. Some postulate the theories have only one. Depending on the complexity, you can have more. What is a scientific theory? Give an example. Let's stick with the kinetic molecular theory of gases. Is the quiz papers gone everywhere? Everyone has a small paper? Okay, good. Everybody's fine. Okay, now I'm going to write down kinetic molecular theory, right? I mean, we just wanted to give you an idea, not an idea. Kinetic which explains okay, I will take gases. Poly laws and everything. What are the postulates? Give you an example. Let's remember. First one was particles in motion, right? Collisions are, what do you call it? Elastic, right? What is the other one?
The energy is proportional to the temperature.
Kinetic energy, right? Temperature in Kelvin, I have to write down Kelvin temperature or Celsius, it's okay. What is the middle one? Right. This side didn't get, only you kind of, you passed by, huh?
Let's go.
Okay. All right. Now, gas laws I wrote down. These are the patterns in data, right? Between volume and pressure, there's a law, inversely proportional. And Charles' law is volume and temperature. Don't try to get the details here. I mean, I'm trying to explain the scientific method, right? Pattern is in observation is called pattern in data. Pattern means regular correlation. It's called the law. Therefore, theory is separate from law. Right? Sometimes people get confused with these two. Right? Scientific law only describes data, right? Not explain anything. Only pressure, volume relations. What is a scientific law? Give an example. What you can say? Well, let's Boyle's law. Okay. What Boyle's law says? Pressure of a gas at constant temperature is inversely proportional to volume. Can you read my handwriting? Pressure of a gas at constant temperature is inversely proportional to volume. I'm reading your handwriting all the time. Right? That's why I put all this on the slide. Okay? Do you understand what I'm saying? All right. Now, how do you mathematically say pressure is All right. So P, how do you do this? How do you remove a proportional thing with a constant? So then you have P1, V1, then P2, another reading, K, V2, then you remove that variable, you get P2, V2. All right, that's how we got Boyle's law in the equation form, right? Okay, so you can use something like that for different cases, right? Depending on the theory. This is a law in kinetic molecular theory of gases, right? Now we want to look at the areas of chemistry. In many subject area like biology, chemistry, physics, don't have everything discussed in under one category because there are different contexts. Gases have different properties, right? Then the things we're dealing with is done separately. Even in chemistry, we have different compounds. Like there are a lot of elements here. The carbon is considered as the element that is fundamental to living organisms, organic matter. So plants, animals, and a lot of material is made out of carbon compound is called organic chemistry. Compounds of carbon, different combination of carbon. Carbon is oxygen, hydrogen, hydrocarbons, all right. Inorganic is rest of the elements. So if you're dealing with compounds other than carbon, like potassium oxide, sodium oxide, ammonium phosphate, there's no carbon. Even a simple like sodium carbonate is considered inorganic because it's not living. Sodium carbonate has carbon, but it's more with the carbon dioxide, closer to carbon dioxide. So this is considered right. And biochemistry is, this will include all the petroleum products, all the gasoline, non-living organic matter, right? That is found in deposit, the oil deposits, crude oil, we refine them and get different gases, natural gas, everything. But the biochemistry is compounds of living systems, right? When you study living systems, we mainly get the compounds of different compounds. So biochemistry deal with large molecules, enzymes, right? ATP, ADP, nucleic acid, all this stuff that make up the living system. So we deal with that in biochemistry. Physical chemistry is, for example, kinetic molecular theory is quantitative. Quantitative means they have formulas, equations, more theoretical. So, see, theoretical concepts of chemistry like kinetics are mainly in the kinetics means how the reaction takes place, and equilibrium, how the reaction a reaction can be in equilibrium with reactants and products. Physical chemistry. Analytical chemistry is like, as the name implies, is the looking at things, analyzing things, elemental analysis, spectroscopy to identify certain metal atoms, lead, mercury, things like that. So this is something to do with instrumentation mainly, and the method of analysis. There are standard procedures. So these are the basic ideas, areas. Okay. So what you're going to do now? Write down all these areas. What is the first one? Inorganic, organic, chemistry,
Biochemistry.
biochemistry, physical chemistry, analytical chemistry. There are also industrial chemistry. Some deal with plant the processes. There could be many sub branches. Okay. All right. Catalysis is industrial chemistry. All right. Let's see whether you can put in the right category here. Research and analyze water sample for lead content. And then analytical chemistry. Can you write down? Okay. And undergraduate studies the allotropes of phosphorus. Inorganic. Allotropes means there are 3. What is allotrope? The same element, right? Multiple forms. Because of the structure, they have similar different properties like carbon, diamond, graphite, buckyballs. Robert Boyle studied the effect of pressure for volume of a gas. Physical chemistry is kind of a mathematical more. Alexander McCain discovered penicillin from fungi and later it was synthesized in the lab. Biochemistry. Researchers starting from simple organic compound, synthesize complex drugs. Organic chemistry, like a pharmaceutical. See, that's another branch, like applied branch of chemistry, pharmaceutical. Right. Okay, you got the idea. Now we're going to look at the properties of substances. We got the scientific approach, but and the areas of chemistry. Now, what is a substance? What is a substance? They have constant physical and chemical properties. If somebody asks us what is a substance of matter, matter that have constant composition, physical properties, and chemical properties are called substances, right? So physical properties are what, like mass, color, density, all this stuff, melting point, boiling point, right? Which we describe material. If you take a pure substance, which is water, you have same composition, same color, same density, same viscosity, boiling points and melting points. The water is same. It's a pure substance. Then chemical properties, water is different from any other pure substance. Water react with sodium, right? And there are many reactions water can undergo, right? So chemical properties. It's specific to the atoms making up the substance, all right? Now you had to guess this. Substance could be further classified into elements and compounds, all right? Elements, if you take an element like oxygen, its physical properties as oxygen is always same and chemical properties always same. If you take water, same. But what is the difference between oxygen and water? Oxygen is an element, right? So therefore, pure substances could be matter, the pure forms of matter made up of one kind of element, right? Atoms of an element, only one type of atoms of an element. That compound is more than one element. Right? It could be 2, 3, 4, 5, 6. All right. Now, this is the idea. Matter is variable composition. Now, if you have a variable composition, means depending on the where you pick that up, if the composition means oxygen, if you take oxygen everywhere you take that, composition is always oxygen, 100% oxygen, right? So if you pick up the small gas samples from here, it could be heterogeneous because different depending on how I breathe the air. Right now, it may be different from where the space you are breathing, right? So that is a variable composition, right? So now, if it is yes, variable, that's a mixture. If it is no, that means it's a pure substance. Composition is same, made up of one type of particle, all show the same physical. And this particle could be atom and a molecule, right? Or ions or whatever it is, metals. All samples show the same physical and chemical properties. Now, made up of multiple type of particles, that means it's a mixture like nitrogen, oxygen, carbon dioxide in a gas sample is a mixture, right? Like that. So therefore, matter could be divided into mixture when they are composed of more than one pure substance, right? Pure substance could be element, two elements together will be a mixture, or element and a compound together, right? Also, we classify mixtures as homogeneous and heterogeneous. That means uniform means, again, the composition. If you have a mixture, I had to go back here. This look a little like, if you take garbage as your example, variable composition, if you take garbage from different places, right, don't have, that's what I'm trying to say, right? So a mixture means variable composition, right? But we can have some mixtures, variable composition, but the composition in different part of that particular mixture, right? Not compared to different garbage. For example, sodium chloride is a solution. Sodium chloride solution could be 100%, 5%, 20% different concentrations, right? But still it's homogeneous. The homogeneous is when things are mixed up thoroughly, right? Gas samples in a small volume are mixed up really well. That's the homogeneous. In a solution like sodium chloride or sugar in water, everything is broken down to molecular level, ion level, so they're homogeneous. Heterogeneous is there's no fixed composition, like a garbage can. If you pull out a piece from the top and the bottom, it's not going to be same, right? Because even the heterogeneity also refers to phases. For example, ice and water, right? Ice and water is a heterogeneous mixture because they are made out of two different phases, right? Even though they are still the same compound. Let's see. What are homogeneous or heterogeneous? Blood? Homogeneous. If you look at it in a microscope, it's borderline, right? There could be large particles. I would say homogeneous, right? Because we cannot see. The composition is same if you take a large blood sample, right? But it's kind of a tricky question. It's homogeneous. Urine, homogeneous. It depends on where the urine is coming from. Sometimes the urine could have suspensions, all right? I mean, if you're sick or something, you have kidney problems, you know. So normally urine is homogeneous. T-bone steak And they are a big piece of bone and all that. Gasoline, homogeneous. If you take a particular sample of gasoline, it's homogeneous. It depends on the gas station though, but Twinkie, salad dressing. Salad dressing is kind of a, it has particles, right? Okay, that's right. Okay. Homogeneous, heterogeneous. Let's go to this. I'm not going to tell you this question again. This is a simple one. Classification of mass. What is a mixture? What is a mixture? You have to sit and tell somebody a mixture made out of two or more substances, pure substances. Okay. Describe it generally. Example. What would be the example?
Chocolate milk.
Chocolate.
Salad dressing.
That's kind of a, yeah. Too late.
Sodium chloride.
Milk, salt water, right? So sodium chloride itself is not a mixture, right? It's a pure substance. Okay, let's get that out. Okay, and what else?
Steel.
Steel.
Yeah.
Steel is an alloy, okay? It's kind of a tricky thing. Like in the iron lattice, you know, you have, it may be think as like a bronze, okay? Let me think about it. Bronze is a mixture, so steel goes, all right? I thought about it, okay? I don't just shout my answers, okay? Like I follow that rule, you know, when they classify for, they're made out of carbon and the iron, right? All right. Okay, we done it. Homogeneous mixture. What is a homogeneous mixture? How do you define it?
Uniform composition.
Uniform composition throughout the sample, right? I throughout the sample, I am not going to write down. So, what is the example? Salt water. It has to qualify for the mixture, criteria of mixture, as well as the homogeneity, right? Water, all right. Heterogeneous mixture. Different compositions. What is the example?
Wet sand.
What did you say?
Wet sand.
Wet sand. Okay.
That's what the book says.
I had to think about, like visualize and conceptually I had to test it. It's water in there and the sand. And, okay. It's not molecularly, like in a solution, they are not dispersed. You mean that's the criteria, right? From different part of the sample, you can pick out the sand and some water, right? So that qualifies. Okay, what is the other thing? Okay. Okay, I will go for that too. Okay. Did I spell it right? Okay. All right. I sound like the vice president who spelled the potato. Long time ago, there was a. Okay. Classify following homogeneous, heterogeneous mixtures. Salt water. Homo.
I'm not trying to.
Okay, chocolate with hair. What is handful of soil? Vegetable garden. Oh my. We have to have a gender equality here, right? Close soft drink bottle. Okay. Just open is where there are froth coming out of the gas, right? So that's the head. Right. Okay, we done with this. Okay, you're going to submit this next class period, okay? And I did that yesterday. Okay, that's what we're going to talk about. Now there are three different states of matter. Common, there's a fourth state, this is called plasma with very high temperatures, which is not that common on the earth, all right, we don't talk about it. Now there are certain properties. Solids have rigid shape, fixed volume, external, okay. Now these are based on kinetic molecular theory of matter. You can describe all these things. Liquids have no fixed shape and fill the container completely, not take the shape of the container. Gases expand fill their container. This has good theoretical understanding. There are a lot of gas laws, but liquids and solids are a little more complicated than gases. How many states of matter? What is the state of matter? If you take a particular substance, element, or compound, it can exist in three different forms, right? What is the state of matter of oxygen? Gas. Okay, you got the idea. Sodium chloride. Ionic compound. Right. Now you guys are going to read the book. We're going through this. Elements and compounds. What is inside the blimp, Goodyear blimp? Helium gas. This is not the outside coating is not the one we are talking about. This is the container of helium. Right? The compound. We are not talking about the glass. Glass is not the focus. Our system is surrounding and the system as surrounding. Universe is system as surrounding. The system is in the side. This is the beach. Why is heterogeneous? There are water, there are sand, right? And homogeneous because it's all in the liquid phase, right? Okay. So this is how the caffeine molecules, right? And some organic molecules, and these are water. It's a complex mixture, but it's homogeneous. See, this one has, even though this is sand, okay, this is water. Okay, this is homogeneous, pure water. You can see conceptually, you know, how they're made up. Helium is here. All helium molecules are monoatomic. All the noble gases have one atom. Independent, the particle that have independent existence is called molecule sometimes, right? That's a helium molecule is the atom. Describe the classification of matter based on composition. State of matter. You have gases, liquids, solids. Okay, composition. What you can say if a different composition, heterogeneous. There is a mixture, right? Mixture, different composition, right? It's a mixture. And the heterogeneous, homogeneous. Okay, all these. Based on composition, mixture, pure substance. If it is composition, is like mixture has different composition and same composition, pure substances, right? Then this one has elements. Compounds. All right. So that's how you explain the, right. There could be gaseous, like a garbage can is mainly assuming there's no liquid there. It's a solid state mixture, right? For this table here, solid state. Okay, but it's a heterogeneous mixture. There are a lot of structure. Now let's define these things. What is a pure substance? We talked about it. Pure substance, how do you, if you have to say what is a pure substance, what is the best description of pure substance?
The same type of atoms or molecules.
Okay.
There's only one type.
You can define that on a atomic scale or macroscopic scale, right?
Like all the atoms are the same, all the molecules.
Yeah, that is atomic scale description. Then how do you describe? We don't deal with atoms all the time. How you deal?
Same properties.
Same physical chemical properties, right? Same composition, right? Then that is kind of conceptually they are made out of. You understand what I'm saying? There are two ways, right? They have same physical and chemical properties. All right. Same composition. That's like a macro disk. Then the nanoscale. This is like a small scale. Same. Ion. All right. So that ion is very small, but there are two ways to describe it. You know, you're conceptually or through the observation, like physical, chemical. What is a chemical element? Describe generally and give an example. It's a pure substance, always, right? How do you write down? It's a pure substance. What distinguishes it from a compound, you know? Made up of what? Now we cannot distinguish a molecule, element and a compound by physical means. They look, the properties look the face. Now you have to describe it by nanoscale description made out of only one. Made up of atoms or molecules. For example, if you get this helium, example, helium, and example, oxygen. This is the atom, this is a molecule, right? All right. What will be a compound? I didn't ask that question. What is a compound? Chemical compound.
More than one element.
Right. Pure substance, atoms or molecules or ions. Okay. Okay. Atoms. Okay, that's fine. This is like what is it? What do you call it? Atoms or molecules, ions of atoms of more than one element, right? More than one element. So water, example, sodium chloride, you can see that how there are two different elements, right? Okay. Okay, we're going to do the quiz now, all right? Okay. Maybe I need to make it because I cannot ask you to drag down. Okay. 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 How many choices? You can write anything, right? This is the quiz question 1. Is it say 1 or A?
One.
You pick A, B, C, D or something.
What are the letters? The one.
What is a mixture?
Which one or what is it?
Wait, you want us to tell you which one is a mixture?
Which one is a mixture?
Is that what you
Is it
There's more questions.
no, just I'm asking. Write down what is a mixture.
like which answer choice is a mixture?
Yeah.
Which
Is it
one?
mixture? Is it mixture?
Okay.
Okay. Is it mixture? Right. There are two answers if you want to see that. You see that?
Both or do we just put one?
No, just write A and whatever.
You want both answers or just one?
Both answers. A and C. Okay, I'm just coaching you, okay? Okay. Now this would have been like this. Mixture here, element there, right?
That's a
Mixture there. Okay, what did he say? Oh yeah, I'm right. Okay.
I hope so.
Come on, dude, I gotta get
Second question. Second question.
This question should.
What is homogeneous?
Okay, which ones are homogeneous? Yeah, you gotta do this.
Okay, let me.
That white rice.
Mag-
One line.
White wine.
It's a little too small.
Dude, that's
There you go.
There you go.
All right. ABC. White wine, magnesium.
Magnesium. Magnon.
I don't know what that
No,
is.
that's a magnesium.
Magnolia.
Okay, Magnon.
Magnesium. Sugar syrup, potato salad, granite. What is the homo?
Syrup, you can't see this.
White wine, one.
Is there 2, 3, 4, 5?
Okay. I did that yesterday. Okay. Okay, that's what we're going to talk about. Now there are 3 different states of matter. Common. There's a 4th state. This is called plasma with very high temperatures, which is not that common on the Earth. All right, we don't talk about it. Now there are certain properties. Solids have rigid shape, fixed volume, external. Okay. Now these are based on kinetic molecular theory of matter. You can describe all these things. Liquids have no fixed shape and fill the container completely. Not take the shape of the container. Gases expand fill their container. This has good theoretical understanding. There are a lot of gas laws, but liquids and solids are a little more complicated than gases. How many states of matter? What is the state of matter? If you take particular substance, element, or compound, it can exist in 3 different forms, right? What is the state of matter of oxygen? Gas. Okay, you got the idea. Sodium chloride. Solid. Ionic compound as well. Right. Now you guys are going to read the book. We going through this elements and compounds. What is inside the blimp? Goodyear blimp? Helium gas. This is not the outside coating. Is not the one we are talking about. This is the container of helium. Right. The compound. We are not talking about the glass. Glass is not the focus. Our system is surrounding in the system as surrounding. Universe is system as surrounding. The system is in the side. This is the beach. Why is heterogeneous? They are water, they are sand, right? And homogeneous because it's all in the liquid phase, right? Okay. So this is how the caffeine molecules, right? And some organic molecules, and these are water. This is a complex mixture, but it's homogeneous. See, this one has, even though this is sand, okay, this is water. Okay, this is homogeneous, pure water. You can see conceptually, how they're made up. Helium is here. All helium molecules are monoatomic. All the noble gases have one atom. Independent, the particle that have independent existence is called molecule sometimes, right? That's a helium molecule is the atom. Describe the classification of matter based on combustion. State of matter. You have gases, liquids, solids. Okay, composition. What you can say for different composition? Heterogeneous. There is a mixture, right? Mixture, different composition, right? It's a mixture. And the heterogeneous, homogeneous. Okay, all these. Based on combustion, mixture, pure substance. If it is composition, it's like mixture has different composition and same composition, pure substances, right? Then this one has elements. Compounds. All right. So that's how you explain the, right. There could be gaseous, like a garbage can is, mainly assuming there's no liquid there, is a solid state mixture, right? Or this table here, solid state. Okay, but it's a heterogeneous mixture. There are a lot of structures. Now let's define these things. What is a pure substance? We talked about it. Pure substance, how do you, if you have this say what is a pure substance? What is the best description of pure substance?
The same type of atoms or molecules.
Okay.
There's only one type.
You can define that on a atomic scale or macroscopic scale, right?
Like all the atoms are the same, all the molecules are the same.
Yeah, that is atomic scale description. Then how do you describe? We don't deal with atoms all the time. How you deal?
Same properties.
Same physical chemical properties, right? Same composition, right? Then that is kind of conceptually they are made out of. You understand what I'm saying? There are two ways, right? They have same physical and chemical properties. All right. Same composition. That's like a macro disk. Then the nano scale. This is like a small scale. Same. Ion. All right. So that ion is very small, but there are two ways to describe it. You know, you're conceptually or through the observation, like physical, chemical. What is a chemical element? Describe generally and give an example. It's a pure substance, always, right? How do you write down? It's a pure substance. What distinguishes it from a compound, you know? Made up of what? Now we cannot distinguish a molecular element and a compound by physical means. They look, the properties look the face. Now you have to describe it by nanoscale description made out of only one. Made up of atoms or molecules. For example, if you get this helium, example, helium, and example, oxygen. This is the atom, this is a molecule, right? All right. What will be a compound? I didn't ask that question. What is a compound? Chemical compound.
More than one element.
Right. Pure substance, atoms or molecules or ions. Okay. Okay. Atoms. Okay, that's fine. This is like what is it? What do you call it? Atoms or molecules, ions of atoms of more than one element, right? More than one element. So water, example, sodium chloride, we can see that how there are two different elements, right? Okay. Okay, we're going to do the quiz now, all right? Okay. Right, let's start on this. I think I went over this, right? Where did you go over this? No. Okay. How about this? Did we? Somebody say we did. Okay, what is a pure substance? What is the definition of pure substance?
Same physical and chemical properties and same composition.
Right.
On like the macro scale. Then for nanoscale, you said atoms or ions or molecules are the same.
Man, you're catching up. This is good. Macro scale. That's good. See, now that's what sometimes we describe in one way. We think that's the only way. But there are macro scale description like physical properties, right?
Yeah.
And the atomic scale or nanoscale is atoms. Pure substance is particles of atoms or molecules, right? Only one kind of them are there, right? So that is right. Did you hear that? What we said there now? Same chemical, physical properties, chemical, physical, chemical properties, and the made up of same substance, either elements or compounds, right? Elements or compounds. Elements are made out of the same type of atom, and compounds are made out of particles consisting of two or more elements, right? What are the examples? For the, like oxygen, all right? Water, sodium chloride, you can name thousands of them, isn't it? Okay. All right, you got it. What is a chemical element? An element is a pure substance, which is one that have same physical and chemical properties, but in the nanoscale, all right, it has only it has the substance, pure substance, which consists of only one type of atom, only one kind of atom. That means atoms from one element. All right? Can you write that down? Okay. So give an example. Let's go to oxygen is too common. How about sodium? All right? Anything in the periodic table is an element here, right? So you can pick up. These are made out of atoms with certain atomic number, right? Okay. All right. They all have the one element have same physical and chemical properties. For example, sodium is different from oxygen. Sodium has different chemical properties. Reactive with water. Oxygen doesn't react with water, like something like that. So sodium, copper are the elements. Okay, what is an allotrope of an element? Describe it generally and give an example. What is an allotrope?
An element that can exist in two or more forms.
Yeah, an element that can exist in two or more different forms because of the connectivity or the bonding in the different ways of connectivity or bonding that they can have. Okay, that means same atom, same type of atom, but they are bonded differently, all right? So therefore they get different chemical and physical properties, right? Now give me an example. Diamond, what is the other one? Diamond is
Carbon.
graphite, coal. Coal is kind of an amorphous carbon, sometimes it could be graphite, all right? Amorphous carbon means there's no structure, powdery carbon, right? Or buckyball, or that spherical with molecule with 60 carbon atoms called buckyball, right? Phosphorus has red phosphorus, gray phosphorus, forgot yellow phosphorus. Okay, the phosphorus has about 3 different allotropes. Oxygen has 2 main ones. What are those? Ozone and oxygen, all right? O2 is one molecule, and in oxygen, O3 is ozone. There are 3 atoms, therefore structure is different, right? Same type of element, all right? Got it. What is a compound? And give an example. What do you know about compounds now?
Composed of 2 or more elements.
Right. Macroscopically speaking, they are pure substances, right? Have constant physical and chemical properties, but their structure or the substance is made out of particles or the molecules or ions from 2 different elements, right? 2 or more elements. So give me an example. Water, sodium chloride, glucose, right? Glucose has 3 different elements, right? Carbon, hydrogen, oxygen, but they are, right? They have distinct molecules of glucose, right? Okay, these are compounds. Okay, let's see this one. Now, changes could be physical or chemical changes. I'm just showing this. This is the macroscopic scale. Carbon dioxide, a piece of carbon dioxide is called dry ice, all right? Dry ice can sublime, right? Sublime. What is sublimation?
Want to go straight from the solid to the gas?
Yes. The phase changes are called melting, solid to a liquid. Evaporation is solid to a gas. Gas to a solid is condensation, right? There are different ways. Melting, then freezing is other way around, right? Liquid to a solid. So this is sublimation. Like if you look at this, if you can read this, let me make it bigger. Okay. This is macroscopic. This is nanoscale. Microscopic is under the microscope, right? See, this is solid state. Regularly arranged carbon dioxide. There's a cube in here. These are the free carbon dioxide atoms. Okay, but this one doesn't correspond. This should be here and here. Like carbon dioxide gas is this. You see that? Yeah. Right. The book should have done it other way. All right. Anyway, I'm not sure what is in the book, but that's the slides they gave me. Okay. Now you see that there's no bonds broken between carbon oxygen atoms. It's only the intermolecular forces, right? Broken. What is intermolecular forces? Forces between the molecules, right? Phase changes involve that. Phase change. Okay. What is a phase change?
When it goes from
Change
one state
like
to another.
liquid to gas, or like
Right.
solid.
Changes between the states of matter, gas to liquid, liquid to gas. Right. Okay. You see that's a physical change. Now, in a physical change, matter didn't, see, it's there. Matter remains the same, right? Only the form, distance, the mainly state of matter. Now you have a different example. This is glucose, sucrose. Sucrose is sugar, table sugar. It's not glucose. How many of you know that? Sucrose is not glucose, right? Sucrose is glucose plus fructose. I mean, later you fructose. So this is in solid. This is, what do you mean by AQ? Aqueous means water solution. So this is, you're adding sugar. That's macroscopic. What is this now? This is the sugar molecules in the solid state, here. This one is right. Then this one is in the, the dispersion. What is dispersion means? Distribution, right? Distributed in the water. Can you see water molecules? All right. Did the substance change here? It's a mixture, but there are two substances. Their bonds didn't break, right? There's no physical. This is physical change. There's no chemical change. How many of you see that? You have to always compare, what is you observing in the macroscopic scale, and we have conceptually we don't see atoms and molecules, but we know that's what's taking place, right? Okay, burning propane. Propane is C3H8, 3 carbon atom hydrocarbon. This is the balance equation, carbon dioxide and water. Okay. When you burn, this is the propane. This is the gas. All right. This is the propane. Propane in the gas. These are C3, 3 carbon atom molecules. And when you burn, that's what happened. What is this? Carbon dioxide. This is water. All right. So that is what we think is going to take place. Can we see them? Like with a naked eye when you're looking at? No, we are in a different domain, right? So, but we have evidence, that is taking place, right? Okay, how many of you got the idea that substance change in here? Because it was before that and this is that. None of those above didn't change, right? Okay, you got some idea about, okay, let me go. Now I'm going to talk about first physical change. The substance does not change into a new substance. Water going into gas, steam. These are the physical properties. Now, physical properties are associated with physical changes. Density. Density is no changes. Then what is density? Right. It's a specific property. Water has certain density. You can identify materials. Remember that Archimedes, however he discovered that gold, the throne, the crown of the king was really made out of gold, or somebody adulterated it. Remember he got the idea that what was the he came out of the bathtub, he went in, then he knew that amount of water. He got the idea. So then he could tell whether the same amount of water is replaced by the same amount of gold, right? It's different in other cases. Okay, because the density is different when you adulterate or they mix the gold with copper or anything else. Color and intensity is a physical property, right? Physical property. For example, sulfur has yellow color. Water is colorless, but there are different colors. Particle size is a physical property because you can break things up. This is a physical change. You can break up a certain thing into small particles, still the same thing. There's no change in substance. Melting and freezing point, there's no change in substance. Boiling point is liquid to gas, right? Steam. Texture. Texture is how you feel on the surface. It could be polish, it's still the substance they change, right? These are some of the, but most common is density, melting point, and boiling point that we use to identify. Okay. Now, some of the properties are used to separate mixtures. For example, I listed some of the physical properties. What are those? Density, color, particle size, melting, boiling, and melting, freezing, boiling point, and the last one is texture or something, right? So how do you use some of these properties to separate mixtures? It depends on the mixture. If you go into a plant with separate, recycled stuff, right? First thing they do is they float the material. Metal goes down. Lighter plastic comes out on the top on the water flotation, float, right? Then you can separate. That is based on density, right? So can you write down something? The density is the one that used in the flotation techniques. Can you come up with another one? Can you separate stuff from color? I never heard any example. You may know it, but I'm not sure how the color can change something, could be used. It's only observation, right? Like you can identify even when they're separated, right? What is the other one on the list? Particle size? How do you use particle size? Size. Sieve. Sieve. What is a sieve? It's a strand. Like a sieve is a mesh. There are different mesh sizes, right? How many of you heard about this word, sieve? Okay, that is called the different sieve sizes are like ASTM, American Standard of American Standard of Measurement and Testing has different sieves. You can grade certain things according to particle. There are sieves which micrometers, some micro, and then 10 microns, the diameter sizes. You can sieve or strain. I'm not sure about that word. Okay, you can separate. All right. What is the other one?
Melting point.
Melting point. All right. How do you separate melting point? Now, give me an example.
Maybe
Salt water melt. Ice comes out, right? Like when you melt salt water, there's no solid solution, with salt and water, right? You can freeze it. Like in the ocean, when it freezes, water freezes, you have icebergs, right? So iceberg. That's one way. I would say like if you have a mixture of iron and wax, it would be ideal, right? Iron powder trapped in wax. What do? You just melt it and maybe filter it, right? Okay. I never thought about that. Melting and freezing. What is boiling? This is most commonly used.
Melting salt water, boiling salt water,
Right, what is this called?
desalination.
Boiling. There's a chemical process. We use the boiling point to evaporate things. This is called distillation. You heard about that? Distillation? What is distillation? You heat a liquid up and condense it back, right? Okay, that's distillation. You can separate salt water from water from salt water. You distill, then salt water going to be on the flask, right? Okay. Now, what is the last one we had? Texture. I'm not sure about that, like the color and texture is not very useful. But there's another one, magnetic properties. You heard about that? Magnetic properties is, we didn't talk about it. Magnetic properties could be used, that's a physical property, magnetic property, all right? Magnetism. How do you separate sawdust from iron powder? So you take a magnet and then all this iron powder will get stuck to the magnet, right? All right. So whole idea is, being chemist or scientist, you need to separate. Yes.
Could you use color like how like different flammable liquids when they're on fire, they're different colors?
Say that again.
What color? Could you use it like different flammable liquids have a different color when on fire?
We can tell the difference, right? But if they are together, I'm talking about separation, right? It could be, all right? Then maybe again you can burn it at a lower temperature. One thing that is kind of a chemical way to do it, right? Burn out. Yes.
For color, could you consider diffraction of light color?
Diffraction. No, we can see the difference between different materials. Would the diffraction move particles separately out of each other? Hey, I don't have an example, right? So that's what you are here, you think about it. I knew some people move atoms by laser. The atom by atom, you can you move with the laser beam. I heard about that. Now we got one, all right? Yeah.
What about chromatography?
Chromatography. Yes. That's a good one. But it's the color is not the one that's separating. It's the physical properties, all right? How does the chromatography work? There's a mobile phase, right? What is chromatography? Like you have a piece of paper, then you put an alcohol solution, you put on a chlorophyll. How many of you seen this in science fairs? Chlorophyll is separated. Then as this front moves, there are different colors, like yellow color, carotenoid, chlorophyll is greener, right?
Isn't that chemical though?
No,
It's not chemical?
this is not chemical. Whole idea of the chromatography is affinity for the paper for different colors is different, right? These different chlorophyll and carotenoids hold on to the paper to a different extent. Then you have a wave, waterfront, right? Washes them out. That those who are holding to the paper strongly, all right, are lag behind and others are passed out. See that? That is how the chromatography. There could be different types of chromatography. Same thing, same idea. It's called affinity separation. Affinity chromatography. Affinity means between the one phase and the different affinities for different substance for a certain kind of a solid phase, right? Then you can use gases too as a mobile moving front, or the liquids, all right? So, all right, that's good one. But it uses the color, but it's not the, it's only thing we see color is being used, right? Okay. All right. Good. We came up with a lot of ideas there. Okay. Now I wanted to briefly, all right, get you to understand, this is not in the book, but I thought this is important for people who are studying fresh, okay? In 100, get an idea how the elements are given symbols. In the periodic table, we have a lot of elements, about 92 stable elements, maybe 83. And the 83 plus all the ones in the black, the ones in the what is that typeface is called? Like this.
Outline.
Underlined or
Outline.
outline typeface. Outline typeface, they're not stable. They're not on Earth, like a technetium. And all these. There are about 92, the ones that which we find on Earth, right? All these black ones, and the green one, the blue one, and the red one are found on Earth. What is that blue ones? Liquids. The gases are red ones. Black ones are solids, right? Okay, these are names given for. How do you give a name to an element? Once the element is discovered, it has same physical and chemical properties, then you give a name, different from all others. So arsenic is, you get the element in first letter and the second letter. Why not argon? First letter is always capital, right? Why didn't we give argon for arsenic? Ar. Ar is already taken up by what? Argon. All right. So therefore arsenic is AS. Barium is straightforward, barium second letter, calcium, carbon, we give first one. Chlorine is Cl. I don't know why chlorine is not called CH, okay? But somehow they come up with Cl. Now these are done by a committee, International Union of Pure and Applied Chemistry. They meet in certain place. Okay, just like this. This is a macroscopy. Inside you have internal energy. Internal energy is nanoscale energy. Internal means inside this has atoms and molecules, right? Still there's internal energy. Now, there's a law called first law of thermodynamics. How many of you have heard about this? Energy neither created nor destroyed. Okay. All matter possesses energy. The matter, normally we have energy, our molecules are moving around. There's a temperature, right? Temperature is kinetic energy. How many of you know that? Temperature is kinetic energy at the internal energy level. All right? Some small particle, one rock, inside there's a temperature. And also, when a particle like ice melts, there's an internal energy release by freezing that can crack a lot of force, right? The rock, the ice trap, the water trap between a rock, when they freeze, they split the rocks, right? So that's how you get the rocks weathered into soil, gradually. Now, kinetic energy is due to movement. Kinetic energy is F_mv squared. What is that? M. Mass times velocity. Now, physical potential energy is like if you have something, it depends on the gravitational constant, mass. Now, these are all macroscopic energies. But if you look at an atom and a molecule, for example, it's a water molecule here. That is kind of a potential energy. If you break up two oxygen and two hydrogen molecules, you need this is lower potential energy here. The potential energy is released. Now, where's the potential energy is in now? It's in the bond, right? Bond. It's just that this one potential energy is in the height, right? And also temperature of water has the kinetic energy, right? So therefore, it applies to internal energy. Internal energy is inside energy, right? So in all these physical and chemical changes, we have energy involvement. When the water gets boiled to gas phase, it doesn't happen automatically. You need to provide energy, right? To break up intermolecular forces, you have to provide heat, right? That amount of heat given is proportional to amount of the water converted to, right? So therefore, it's conserved, all right? So we need to think about all these changes, changes in matter, both physical and chemical, gaining or releasing energy. Gas going to a liquid releases energy. So these energies should be provided or released into the environment, okay? They're conserved. Energy is capacity to do work. Okay, this is more in the macroscopic description. Okay, let's look at this last question. What is law of conservation energy? How it applies to physical and chemical change given below? What is law of conservation energy? Energy is neither created nor destroyed, it's conserved. Okay, in this case, higher energy. The higher kinetic energy. Lower energy. Now, where does that energy come from? The liquid doesn't get converted spontaneously to gases. Heat. You have to have heat, all right? Heat from hot plate, whatever it is, heat should be coming out. So this heat is in kinetic energy now. You see that? Okay, when you burn, this is physical change. All right? Physical changes require some heat source, right? Okay, chemical energy is, once the reaction gets started, the bonds are broken. Here. That is the oxygen. That's the carbon. That's the water. This is heat. How many of you know that if you burn methane, you get heat? Methane is natural gas, right? Where does that heat come from? There's no outside heat source. It came burning. Where was that energy before and after? Bonds. So bonds break and form. Bonds break and form. Now, if this side bonds are broken, bonds are formed. If this side is more than that side, it's endothermic, negative heat. Do you understand that in a chemical reaction, heat could be given out or released? So where does that heat come from or absorb? If it is exothermic heat given out, that means this side has more bond energy, which is broken up, they form less bonds, therefore heat is released, right? And if you are endothermic reaction, bond energies on this side are much more than this side, therefore there's a deficit of energy, right? So it should be absorbed, right? All right, from the surrounding. Okay. How many of you got the idea now? Then we are done with the chapter, the second homework, okay? That's the last question, right? Okay. You bring that to me next week, okay? No, Wednesday. Next week is too late. Okay, how many of you have which paper?
No, this is that's homework four.
Everybody has a quiz paper, small paper?
We need papers.
Okay. Where is those paper? Everybody signed the class roll?
No.
Man, I've been so nice to you guys. And I was just trying to get, where did it get started? Where's the quiz? You guys have to take care of yourself. You have to tell me I didn't get the quiz or the paper, right? The class roll. And you guys make sure that it went to this side, right? Okay. Did this guy side got that? Okay, how come only they don't like you? Yeah. You kind of A student. Great point. All of the following properties of a substance can aid in the identification except. Got it?
No.
I'm thinking. I didn't do anything. You can. All are here. All right? Did you get it?
Good.
All right. Who had a problem that needed more time to do it? Yeah. I shouldn't point out anybody. Okay, which of the following will not have a specific composition and a specific property? What do you think the answer is? I'm generous.
Carbon dioxide.
Huh?
Carbon dioxide.
I thought it was aspirin.
Will not have a specific.
Aspirin. Aspirin.
Aspirin is a compound.
Brass.
Okay, sugar is a crystalline substance. We have a boiling point and a melting point. Sugar is
Brass.
right. Why is brass? Brass is not a. It's a mixture. Okay. Brass could be different things, right? Okay. All right. I'm letting you go.